This video is part two of two videos in which we're learning about relations and functions. The concepts explored about relations in the first video will now be extended to functions, so you may wish to watch part one before watching part two. As we saw in part one, these are all graphs of relations. But not all of these are functions. Only ones on the left are graphs of functions. Based on these examples and non-examples, what do you think makes a relation a function? To explore the difference, let's take a similar graph from each column. Recall that for a relation, the horizontal axis typically represents the independent variable, and the vertical axis typically represents the dependent variable. Look at the graph of the function on the left and notice the points corresponding to the independent variable. For each value of the independent variable, there is only one value of the dependent variable. Now look at the graph of the non-function on the right. Notice that for some values of the independent variable, there is more than one value of the dependent variable. So a function is a relation in which each value of the independent variable is related to exactly one value of the dependent variable. In other words, for every x value, there's only one y value. One way to determine a function visually is to do what's called the vertical line test. If I pass a vertical line anywhere on a function, it only crosses the graph at most one time. Yet with a non-function, it passes through more than one point. Let's do the vertical line test on all of the remaining graphs. No matter where the vertical line goes on the functions, it can only cross on at most one point. But with the non-functions, it crosses at more than one point at least once. What about other representations of functions, like a table of values? Can you tell which of these relations is a function and which is not? The first table has unique x values, which is the independent variable, so there is only one y value for each x value. So it represents a function, at least for the points indicated. In the second table, for x equals 2, there are two different y values. In the third table, once again, all of the x values are unique. Even though two of the y values are the same, that does not matter. There is still only one y value for each x value. So this table also represents a function. We can use similar reasoning to recognize functions with other representations too. For example, in sets of ordered pairs. For the non-function, we can identify two ordered pairs that have the same x-coordinate. We can also recognize functions using arrow diagrams. The non-function shows that one of the independent values leads to two dependent values. It's important to point out that when we've been talking about whether something represents a function or not, we've been talking about y being a function of x. In this example, we could say that x is a function of y. What really matters is which variable is independent and which is dependent. And typically we consider x, or whichever variable is on the horizontal axis, to be the independent variable. Consider this next function represented using a graph. We can take points from this graph and put them in a table. As is typically the case, let the x be the independent variable and y be the dependent variable. Another way we can look at the relationship is as input values leading to output values, which we can see when we look at the equation for this function, which is y equals 1 minus x divided by 2. For example, we can input 4 into the equation and calculate the output. Because every input leads to exactly one output, we can say that y is a function of x. A shorter way of writing this is to say y equals f of x. This is what is called function notation, and we can use it to label our graph and the output of our table. The f is the name of the function, and we could use any letter. The x represents the input of the function. So the equation in our function is f of x equals 1 minus x divided by 2. If we are asked to evaluate f of negative 2, this means we substitute the value of negative 2 into x. So f of negative 2 equals 1 minus negative 2 divided by 2, which evaluates to positive 2. So f of negative 2 equals 2. On the graph, this corresponds to the point where x equals negative 2. We understand this point as negative 2, f of negative 2, and that evaluates to negative 2, 2. This also corresponds to the row in the table where x equals negative 2. Let's apply what we have learned about functions to solve some problems. Given this graph of a function, we are asked what is f of 3 and what is x when f of x equals 3? How can you use the graph to figure out the answers to these questions? For the first one, the 3 represents the value of x. On the graph, we see that when x equals 3, then y equals 1. So f of 3 equals 1. For the second question, f of x corresponds to the y value. On the graph, we can see that there are 2 points where y equals 3. So f of x equals 3 when x equals negative 3 or x equals 4. We can also answer questions like these when given the equation of a function. For example, suppose f of x equals 2x minus 5. And because we can name a function using any letter, let's suppose that this question is about g of x instead. What strategy can you use to answer these questions? We could graph the function and use the graph, but we can also use algebra. For the first question, the 3 corresponds to the x value, so we can substitute 3 into x in the equation. So g of 3 equals 2 times 3 minus 5, which is 6 minus 5, so g of 3 equals 1. For the second question, we are given the value of g of x to be 3. So this means that 2x minus 5 equals 3. Solving this equation gives us that g of x equals 3 when x equals 4. For our final problem, we'll start with a wooden board that is 10 feet long and 2 inches wide. First, we'll cut this board in half. Next, we'll cut both halves at another place that is x inches from the right. We will then use these 4 pieces to make a picture frame. Because x is a variable, we can imagine several different sizes of frame that we could make from these pieces. Let's use a of x to be the function that describes the area of the picture that is framed. For this problem, a of x equals the product of x minus 4 and 60 minus x. Recall that the width of the board is 2 inches. Look at the equation of the function and make sense of why this equation models the area of the picture. The area of a rectangle is its base times its height. The frame is 2 inches on each side, so the base of the picture is x minus 4. Let h be the height of the picture. The original board was 120 inches, and removing the top and bottom boards that each have a length of x leaves us with 120 minus 2x inches. But this is the length of the left and right board, so we need to divide by 2 to get the height. So the height is 60 minus x inches. Suppose the board was cut at x equals 36 inches. What is the area of the picture? To answer this question, we need to calculate a of 36. Substituting for x, we get 36 minus 4 times 60 minus 36. That's 32 times 24, so the area of the picture is 768 square inches. Here is a graph of this function. What is its domain? Recall that the domain of a relation means the set of values of the independent variable, which in this case is a set of x values. If we just look at the equation on its graph, we would say that the domain is all real numbers. But in the context of this problem, the area cannot be negative, so we need to ignore the parts of the graph that go below the x-axis. We also don't want to consider an area of 0 because then there would not be a picture. So the domain is as indicated on the graph, which we can write as x is greater than 4 and less than 60. We could have used the equation to get the domain. Because we need a positive area, x must be greater than 4 and less than 60. We can also visualize the domain. We can see that x must be greater than 4 inches and less than 60 inches. The domain gives us a hint about how we could generalize this problem. Suppose the length of the board is L and its width is W. How could we write the general function for the area of this picture? Let's first look at the 4 and recall seeing it as the width of 2 boards put together. So generally, this is 2W. We saw the 60 when the height of the picture was at a minimum. And this is half of the board length, or L divided by 2. So our general function for this problem is a of x equals x minus 2w times L divided by 2 minus x. This video addresses several learning standards and the foundations of mathematics and Pre-Calculus 10 curriculum. In this content standard, we focused on functions. And as we did in the Part 1 video, we have connected data and graphs to situations. As your child learns about relations in their classroom, several curricular competencies may emerge. For example, we used reasoning through classifying to figure out what makes a relation a function. We also used generalizing in the picture frame problem. The same problem is an example of using math to model a situational context. Finally, we represented functions using arrow diagrams, tables, graphs, and with function notation. We hope that you found this Part 2 video valuable in helping you support your child in their learning about functions. Be sure to check out the other titles in this series.